Welcome to this presentation on multidisciplinary design optimization of a mobile miner using the OpenMDAO platform. The work presented here has been conducted by me, Olle Widner, Robert Pettersson, Johan A. Persson, and Johan Elvander. Mobile miners are pieces of specialized mining equipment that can provide a viable alternative to other mining methods, such as tunnel boring machines or the traditional drill and blast technique. As demonstrated in this video by a manufacturer of mobile miners, their main mode of operation is by pushing a rotating cutter wheel against the tunnel wall, thereby continuously excavating rock chips. Mobile miners are complex engineered-to-order products associated with high financial risks. To be able to supply a quotation, one must invest in time-consuming development activities. This asks for methods that can help with making faster, yet accurate predictions of the product characteristics, and with rationalizing the engineering process to reduce lead times. One such method is multidisciplinary analysis and optimization that is commonly utilized by assembling multiple computational models with an integration framework and then using an optimizer to drive the integrated model towards optimal design points. The computational results are gathered into a dataset, which can then be consumed by post-processing and visualization tools to provide relevant information to a decision maker. There are several commercial software packages that can handle most of these concerns within one encapsulated environment. There are also open and closed source alternatives that can handle some of these concerns in a standalone fashion. Most relevant for this work is the OpenMDAO library, along with the NSGA2 optimizer, MATLAB for model definition, the X-array data structure, and some common visualization tools within the Python ecosystem. An issue with using these tools together is that they are partially lacking generic and reusable interfaces for connecting them with each other. To bridge these gaps, we have developed the following open and reusable software utilities. An implementation of the NSGA2 optimizer for OpenMDAO, supporting discrete variables and multiple objectives. A bridge to easily use MATLAB functions as models within OpenMDAO, and a toolbox for recording, post-processing, and visualizing multi-objective optimization data. For more information on these utilities, we refer to the corresponding DOIs. By assembling all of these entities, along with a number of proprietary models, we have created an optimization framework for a conceptual mobile miner. Within this framework, a set of design variables are controlled by an NSGA2 optimizer to find a set of optimal configurations for a given environment or business case. First, a set of intermediate variables are pre-calculated to simplify for other models. Then, the cutter wheel dimensions and the cutting profile are determined together using a nonlinear solver. At this stage, the number of cutters is fixed, but the placement of each individual cutter is yet to be determined. Another internal optimization loop is used here to solve the placement problem. Now we can determine the performance and lifetime of the machine and convert these metrics into objective and constraint values. Here the process starts over with new design variable values. An important property of the framework is that it automatically adapts to changes in the environment variables and the set of objectives, meaning that it can be used to solve many different problems without complicated reconfiguration. Configuring the framework to optimize for maximum excavation rate and maximum cutter lifetime allows us to investigate the Pareto-optimal trade-off between these two important machine properties. The results of such a study will now be briefly discussed. Running on a single standard laptop for approximately 20 minutes, the genetic algorithm has sequentially evaluated the integrated model over the course of 75 generations with 76 individuals in each, 5,700 evaluations in total. Plotting the hypervolume of each generation, we can see that it is initially declining due to elimination of infeasible solutions. After around 10 generations, it takes on a positive trend up until generation 45, after which it seems that the evolution settles somewhat. After termination of the optimization study, we can post-process the dataset by discarding solutions that does not satisfy the constraints, and then by filtering for only the Pareto-optimal set of design points. Plotting these 68 points in objective space shows that there is indeed a trade-off to be made between the objectives. Additionally, we can see that there is one design variable in particular that impacts the performance characteristics greatly. Now, to conclude, we have developed and demonstrated a framework for evaluating and optimizing mobile miner concepts. The generic building blocks used to build this framework has been packaged and made publicly available under open source licenses for others to use and to develop further. Finally, we see this work as a first step towards optimization-supported configuration of engineered-to-order products using open technologies. Thank you for your interest in this presentation and our work.